Okay, video number 4, David Lewis, Trigonometry, 5th year, higher level maths, homework review. We're going to start off with the first piece of homework that you got from me. So it was question 5.6, it was on page 42. What we're going to use this video for is I'm going to show you why I gave you the homework and what I wanted you to hopefully get from it, as opposed to actually just looking at the numbers on the board. So potentially, if you've got this done, this could be a really valuable video to you. If you haven't got it done, I suggest you press pause and then you go home and you go off and you do your homework and then you come back to this. So anyway, the first question here says, a windscreen wiper clears part of a car windscreen as shown below. Great. And now I can instantly see that this windscreen wiper itself is in the form of one of our sectors. Great. Now I'm not going to draw the rest of it up there. It says that the wiper moves in a circular arc through an angle of 105 degrees. That's great because I know most of you guys out there prefer degrees to radians. From its center point O, really doesn't make that much of a difference, but I know just subconsciously we would prefer degrees. AB is the wiper blade, and the bottom of AB is 22 centimeters from O. Great. The wiper blade itself is 60 centimeters wide. Find the area of the windscreen cleared by the wiper. Give your answer correct to the nearest centimeter squared. So the wiper is going like this. It's not getting the bottom part. It's not getting this shaded part. Alright, it's getting the top part, but I'm just going to have it shaded. It's getting this top part here, and we're trying to find the area that is cleared off. Okay, so if you actually put this into a picture, that is actually, the part that we're looking for is, if you took the overall sector and you subtracted the small sector, can you see the small sector down there? If you subtract the small sector, that's going to equal to the weird shape left over. So, something like that. So it's quite akin to the square and the circle idea you would have seen back at junior cert, or even remember we said the whole thing to do with sectors is finding the segment, where you took the sector itself and subtracted the triangle and you're left with that segment. It's kind of the same, but we're just taking one small sector from a bigger sector and left with this shape here. So what do we do? Well, we've got to find the area of each of the sectors, and the area of each of the sectors, that's okay, that's fine for us to fill out, that's just a formula. But from that, we then have to say, okay, are we going for degrees or radians? Well, because they told us degrees in the question, we're going to go with degrees. Okay, so the area of this sector is just pi r squared theta over 360. So pi r squared theta over 360. Okay, same with this. So minus pi r squared theta over 360. And that's going to get me my answer. Now, in terms of the big sector, well, we don't actually have the radius yet. But they've told us that this part here, they've told us that part there is 22. And they've also told us that the blade, so the blade is something like up here, but it's still giving you the same distance, is 60. So if you add those both together, you can figure out that the radius of that sector is 60 plus 22, 82. And then in terms of the angle, well, they told us that that's 105. For the small sector, well, we actually got given the radius, that's 22, and then we also know that that's 105, so it's actually the same angle. So I would set it up like that. I would put in my numbers, so we have 82 squared, 105 degrees over 360, minus pi, 22 squared, 105 degrees over 360. I put that into my calculator and I get an answer. Okay, so I directly put that into my calculator. I actually got 6161 if you did it separately. I put it directly into my calculator, but if you want to do it one at a time, 6161 minus 443, and I got my answer. My area of this wiper blade here, area of the wiper blade was 5718 centimeters squared, because it was an area. Okay, now the reason I wanted you to do that is I wanted you to be okay with using sectors in a practical everyday example, exactly like the 2019 question, which was to do with a trough. Okay, there wasn't a big deal behind that. In fact, it was again right angle triangles involved in there as well, but it was just using sectors in a real life idea. So in 2019, what they actually did was they took the sector and turned it into a trough, but they actually cut off a different part of it. And so they still got that shape, you can think of it flipped upside down, and they put like, I think it was like 5 meters that way or whatever, so it turned into a 3D shape, and we could find the volume of that. And it was really straightforward as long as you're comfortable with sectors. So I thought that was a bit of a weird one, so we should give that a go. The next one was from 2010, question 2b on page 142. Okay, so the reason I like this question is because there's loads of different ways to answer it. So if you go to page 142, it basically is multiple different ways. So the way I do it here, the way that's in the notes, they might be completely separate, they might be completely different. But it's from 2010, part B. It said roofs of buildings are often supported by frameworks of timber called roof trusses. Now, I personally know nothing about frameworks of buildings or roof trusses, but I know loads about triangles, and I can see from looking at that roof truss that there are plenty of them. Okay, so a quantity surveyor needs to find the total length of timber needed in order to make a triangular truss shown below. Okay, so I'm going to try to do this really quickly and draw this up here. Might not be perfect. Oh, turns out it is perfect. So A, D, E, C, G, B, F. Okay, and what do we know? The length of AC is 6. Okay, so all across the bottom, we know that length is 6, and the pitch of the roof is 35 degrees as shown. So that's 6. Great. And that's 35. AD is equal to DE is equal to EC, so they're all the same. So they're all 2. Okay, great. And AF is equal to FB, BG. Okay, cool. So probably shouldn't have had 2 dashes there, but fine. You get the general idea. They're all 2. We have no numbers for the other parts here, but that is the same as that, and that is the same as that. Perfect. Okay, then it says calculate the length of AB in meters correct to 2 decimal places, and this is worth 10 marks, so calculate the length of AB. Now, there are definitely different ways you can do it. You could go ahead and you could use this triangle here, you could find AF, you could jump something in, you could do loads of different ways, but the way I like best is I like always thinking about trigonometric ideas that I have to add something to the question. I want you to get into the habit of adding something to the question. That's why I asked you to do this. I also want you to get into the habit that there are multiple ways of solving questions. So there are definitely a few different ways you could do it, but if I wanted to drop a perpendicular line, now it's not going to look unbelievable on my diagram, but drop a perpendicular line from the top to the bottom, because now I've created one of my famous right angle triangles, and now it's back to junior cert. If you look at that triangle, we're looking for AB here, this part up here. Okay, if you look at this triangle, I'm going to take it out and draw it over here. We have the thing we're looking for, X. Well, the perpendicular, although it doesn't look like it there, we'll cut this 2 in half, so the bottom will be 3 altogether. And we have that this is 35 degrees, and that triangle itself you could have solved in second year. So if you go ahead and solve that using cosine, you'll find that AB is equal to 3.66 meters. Grand. But all to do with just having the confidence to take your time to make a plan, which is what trigonometry is all about. Then part 2 said, calculate the total length of timber required to make the truss. So we've got to find out what all these pieces are. Now, if you think about it, we have this bottom here. The bottom is 6. Grand. We have AB, and we know AB is the same as BC. Grand. So plus twice 3.66. Great. All we have to find is FD and BD. So FD and BD. Okay, how do we do that? Well, if I wanted to find FD and BD, well, let's just focus on FD to begin with. And the reason I'm going to find FD and that's all I need to find is because that's going to be the same as this piece over here. If I take the, and again, multiple ways of doing it, if I take the triangle that FD is in, so that small triangle there, we've got, it's not a right angle for the first time in a while. This is not a right angle triangle. We've got 35 degrees, so 35 degrees. We've got that this is 2, which we were given. And we actually know this. We know AF. And the reason we know AF there is because, well, we found what AB is, and AF is equal to FB, so that cuts that in half. So AF is actually 3.66 divided by 2. So if you took that and divided it by 2, you get 1.83. And if you go ahead now and use the cosine rule, so use the cosine rule because is it a right angle triangle? No. Is there a pair? No. And you find this here, so you find Z, or you find FD, the thing that we're actually looking for. We use the cosine rule to find that. Well, then we'll find out what FD is. And when I did that, I figured out that FD itself was equal to 1.163. Now, I need that length of timber twice, because FD, this part here, is not only here, but it is here. So I'm going to say plus 2 times 1.163. The last piece, which is dB, if I get this dB out and multiply it by 2, we can do it in virtually the same way. We have a triangle, so forgive me for writing at the bottom of the board here, but we've got a triangle going up like that to B, down, AD goes across 35 degrees. We have this as 3.66, we have this as 2, and we're looking for this, so let's just call it Y. Okay, so I kind of jumped to X, Z, Y, sorry about that, but fine, we're going for Y. So if I go to get Y, I use the cosine rule again, I find Y. Y for me ended up being 2.325, so it was the cosine rule again, and then that's plus 2 times 2.325. Add all that together in your calculator, and you should get, correct to one decimal place, 20.3 meters. Now the adding together is not the cool part. The good part is actually the fact that there's many different triangles, and we're keeping our cool and working on them one at a time. And definitely, if you've got a different way of doing it, you might get a slightly different answer, and there definitely is other ways of doing it. That's just the way I've seen it there, and that's why I like that question. Okay, the last two, we've got one on page 111. We're just going to talk through, okay, because you have all the solutions there with you. I just want to talk through what you should be looking out for, and we're not going to do the numbers. So on page 111, just a bit of difficulty here turning the page. So. Okay. This is really like the 2017 past paper question, and if a question like this doesn't come up this year, it will be it will be seriously on my radar for the yearly cert exam. It says a vertical ruined tower stands on one bank of a river. The point P is directly opposite S on the opposite bank. The point Q is 8 meters to the right of P on the same bank of the river. Great. They've got all that stuff written in. From Q, the angle of elevation, 35.8. The point R is 15 meters to the left of P, great, on the same bank of the river. And from R, the angle of elevation of the top of the tower is 23.7 degrees. Okay, now I'd make sure I have all that stuff in there. I'm also noting that it is a 3D piece, isn't it? It is a 3D piece, so I'd probably draw it from above there. Like actually, by probably I mean definitely. And if you look at the shape of this 3D piece, it's exactly like the one we had with our tree. Remember we found the height of the tree? Cool. So part 1 says, let the height of the tower be h meters. Now I know students don't like that. I actually know they actively hate that. Okay? They let something be a letter. Okay, so just pretend it's a number. What would you do if it was a number? If you don't have it in your head that you say, oh, I always mess up when it's a letter, just pretend it's a number. And then go back and do it for a letter. So let the tower be h. Okay, i.e. h or st is h, express qs in terms of h. So let's just go off ahead and find qs. So there's just a triangle there. We've got the height of the tower, we've got an angle, so we can use, it's a right angle triangle, so we can use SOHCAHTOA and then find what qs is. Just has h in our answer. Same way sometimes we have pi in our answer. This is not a problem at all. It then says express rs in terms of h. Okay, fantastic. So that's just another triangle. It's maybe harder to see because of the angle of the question, but it's a right angle triangle. You do the exact same thing. Absolutely no different there. So you have the answers for that. So that's fine. Okay. I know the reason I've asked you to do this, I just know students aren't comfortable with leaving H in their answers. Look at the 2017 past paper question, the exact same. We have to be comfortable with that. And then it says hence. So from what you've done, it doesn't say hence or otherwise, it says hence. You have to use what you have done. So hence, calculate the width of the river PS. Okay, and potentially now, this is where drawing our piece from above will come into play. Because we have the two dotted sides of our triangle, we actually have the base there as well. Okay, but I'm kind of thinking, look, they've told me it's a right angle triangle on the base there. Grand, give your answer correct to one decimal place. Now the way I've seen to do this, and maybe you've seen another way, is I'm thinking, okay, well, if I use some Pythagoras here, and I find the width of the river in terms of h squared, and I do it for one triangle, and then I also do it for another angle, and then I put my two answers equal to each other, that should hopefully allow me to get the SP there. So I don't even have to get h, I've got the two different parts there in terms of numbers, and I can get that SP at the end. Okay, so you use some right angle triangles, you put your answers equal to each other, so you get rid of something. It's a very, very, very long question. You have the solutions, give it a go in terms of the plan. Don't focus too much on the maths of it, but what I want you to take out of that question is giving your answer in terms of h and getting comfortable with that. The last question on page 123, if you give me about 2 years to turn over my pages here, is about the Louvre pyramid. Okay, so this is no different to us. That pyramid's the same as the one in Giza, the same as the made-up pyramid. It's a glass and metal pyramid in the main courtyard of the Louvre. I think that's how you pronounce it. Louvre. Is that how you pronounce it? Louvre. David Louvre. Louvre Palace in Paris. Pyramid Palace. The base of the pyramid is a square. Fantastic. I'm just going to draw from above now. So I'm going to forget that this is the Louvre or anything to do with that. I'm going to draw a square, and it tells you what the side is. I'm going to draw my usual diagonals. The vertical height from the center of the base to the vertex is 20.55. So now knowing our maths language is quite important. We would have seen before the examiner didn't actually, or the question didn't actually say the slanted edge, or that they mentioned something different. In the Leaving Cert, they'll always call it something like the slanted edge. Okay, so just be okay with that. But it said the vertical height from the center to the vertex. So from the base, so the very center of our square, to the vertex is the tip, the top of the pyramid, is 20.55. We know how that could come in handy. So this is the first question. They haven't drawn in the right angle triangle for us. It says calculate the length of one slanted edge of the pyramid. Okay, so that's fine, because we can do our idea from Pythagoras with the base, half it, and then suddenly we have the base of that triangle. So exactly like we've done twice before already. Part 2, calculate the measure of angle A. Okay, so that's fantastic, because now we have a slanted edge and we've got the base down there. We've actually therefore got two slanted edges. We can go ahead and calculate that angle A. How do we do it? Well, it's actually the idea that I tried to not make you do a few minutes ago. What do I mean by that? Well, a few minutes ago in the video there, so a few minutes ago in my time, I asked you to not, so it could be, God knows when it's true, I asked you to not go ahead and find this angle using the cosine rule. In this case, we have the slanted edge. Let's just make it up. Let's just say it's 17, so we know that's 17. And they've told us the base here is, what, 35.42. I told you to not use the cosine rule to get this angle here. Okay, and that's simply because we're going to go ahead and get the area. But there's nothing like saying that we can't go ahead and get it if you wanted to do it that way. So it says calculate that there. Now we've got the triangle, so you just go through your motions. Is it a right angle? No. Okay. Does it have a pair? No. Remember, that's not a pair. You have to have both of them for it to be a pair. Therefore, it's the cosine rule. And if you go ahead and use the cosine rule to find A, you could either use the rearranged version, or you could put it in and do some algebra. We can go ahead and get that angle. Okay, last part, because I don't want you to do part B, we just wanted to do part A. Hence or otherwise, so here if you wanted to, you could do or otherwise. Before, if it said hence just by itself, you have to do hence. Find the area of one of the triangular faces of the pyramid. So if you were using hence, well now we could do half AB by the sine of C. Okay, if we were using or otherwise, well I suppose we could drop the perpendicular there if you wanted to, like we saw in the last question, or you could use the Heron's formula that we spoke about before. Okay, and that's in your formula and tables book because you've 1, 2, 3 sides. Okay, so you can see once you get an idea here of what they're looking for in these trigonometric questions, it's just the same stuff repeating itself again and again. So from our class questions to our homework questions to our past paper questions to our predicted questions, all the same ideas. What have we learned in the 3D pyramids? We've learned well, 3D in general, draw from above, draw your side, right angle triangles come into play, and then in the pyramids, the fact that when we're dealing with Pythagoras on the base, that can be divided into